All right, welcome back, everybody. We'll look at section 3.3, displaying numerical data using frequency distributions and histograms. Basically, the focus is on histograms. We'll talk briefly at the beginning here about what a frequency distribution is, okay? A stem and leaf display is not always an effective way to summarize data because it can be unwieldy when the data set contains a large number of observations. You saw that in section 3.2. Frequency distributions and histograms are displays that work well for large data sets. Um, discrete numerical data often results from counting. Okay, remember discrete are just set values the variables can take on. Anytime we're talking like the number of pets you own or something along those lines, when we're counting, that's discrete. When this is the case, each observation is a whole number. As in the case of categorical data, a frequency distribution for discrete numerical data lists each possible value, either individually or grouped into intervals, the associated frequency, the number of times those values show up, and sometimes even the corresponding relative frequency. Recall that relative frequency is calculated by dividing the frequency by the total number of observations in the data set. Okay, the particular number of values divided by the total number of values. Okay. So basically what we'll do is we'll kind of go through this promiscuous queen bees example, and I'm going to show you how to do these graphs, and I'm going to use the calculator here. I find it easier to use this than, say, Google Sheets for this kind of stuff. I don't really like the way Google Sheets formatting for the histograms works. Okay, so I'll be using this. All right, and we'll go through a couple examples here with this, and I'm just going to make some key points on shape of distributions, and that should be good for chapter 3. All right, folks. So here we go. Promiscuous queen bees. Who knew? Queen honeybees mate shortly after they become adults. During a mating flight, the queen usually takes multiple partners, collecting sperm that she will store and use throughout the rest of her life. The authors of the paper, The Curious Promiscuity of Queen Honeybees, studied the behavior of 30 queen honeybees to learn about the length of mating flights and the number of partners a queen takes during a mating flight. The accompanying data on number of partners on one mating flight were generated to be consistent with summary values and graphs given in the paper. Okay, so in any event, what we have here is the data on the number of partners each of those 30 bees had on their mating flight. Okay, so this is called the raw data. Okay, so one looks like the first one had 12 partners, the next queen bee had 2 partners, 4 partners, so on and so forth. Okay, the relative frequency distribution that I highlighted up above here, okay, this just lists all the data in kind of like a table form, if you will. Okay, here's the variable, the number of partners the bees had. So there were 30 bees. It looked like, if we look at the data, they all had at least one. So that was the minimum number, and the largest number it looked like was 12. Okay, so the variable number of partners, we go 1 through 12. Okay, and then here we have the frequency, the number of bees who had that number of partners. So one queen bee had 1 partner, 1 bee had 2 partners, 1 had 3 partners, 3 of the bees had 4 partners, so on and so forth. Okay, and then finally we have the relative frequency, which is the frequency, each of these numbers, divided by the total sample size, which was 30. Okay, and you see the math over here, 1 over 30, and they go to the nearest thousandth is 0.033. Okay, so again, you just take each of these numbers, divide by 30. For example, 3 over 30 is 0.1 on the nose. There's that. Okay, and here's our relative frequencies. Okay, so then the text talks about using different size intervals. These are intervals of size 1 that we have here. Okay, 1, 2, 3, 4. Sometimes we can group them. Maybe we're interested in grouping the data. How many bees total had 1 through 3 partners? Okay, 3. And that's, again, simply found by adding these 3. How many bees had 4 through 6 partners? Well, if we add all these up, we see that there were 10 bees. Okay, so on and so forth. And then these relative frequencies are now calculated by taking each of these and dividing, again, by 30. Okay. In any event, a histogram for discrete numerical data is a graph of frequency or relative frequency distribution, and it is similar to the bar charts we saw for categorical data. Each frequency or relative frequency is represented by a rectangle centered over the corresponding value or range of values, and the area of the rectangle is proportional to the corresponding frequency or relative frequencies. Again, you've heard me say that in the previous video. Okay, this is how why we use area. Areas of rectangles should be proportional to the frequencies or relative frequencies. So histogram for discrete numerical data, when do we use it? Well, we use it for discrete numerical data, and it does work well for large data sets. We have a horizontal scale, we have a vertical scale that we always use either the frequency or relative frequency for here. Above each possible value, draw the rectangle centered at that value, blah, blah, blah. We're not going to be doing this by hand. Again, we'll be using technology. And if anything, really, the point of this lesson is as you go through your web assignment for Chapter 3, if you have, I think there's a couple where they maybe give you the data set and they ask you to find the correct graph associated with that data set. You could always punch this into your calculator, look at what it looks like on your calculator, and then match it up if you need to go to that route. Okay. Things we look for in graphs or what we call the center or typical value. Where does this thing really peak? How much variability is there from left to right? Is it a lot of values or is it a few values? What's the general shape? We're going to talk a little bit more about that in this lesson towards the end. We talk about the location of the peak, the number of peaks, okay, and if there are gaps or outliers. And mathematically, we're going to get into outliers in Chapter 4. Okay, and in general terms, an outlier is any value in the data that seems unusually high or unusually low compared to the rest of the data. Okay, but mathematically, we'll get to that in Chapter 4. Now, in the text here, they show the histograms. Okay, like here's a frequency histogram. Okay, for the number of partners, you can see they're centered at 1, 2, 3, 4, 5 up through 12, and highest frequency was 7, and here we go. Okay, and if you notice, if you're looking at the graph of the relative frequency, it looks identical. Okay, they're basically one and the same graph, just with different scaling on the y-axis. Here we're dealing with percentages. Here we're dealing with the actual numbers. Okay, but in any event, how do we make these given the data on our calculator? Okay. So I've got the calculator here, we'll turn it on, and I'm going to go into, let's see, we've got our raw data, okay, so here was the raw data back here. Here's our 30 pieces of data. So I'm going to go into stat, and I'm going to go into edit. And I've actually taken a moment to do this, and I'm just using L4. Most of you will probably use list 1. Okay, I just used L4. I'll explain why a little later. It's not a big deal. And I put all 30 of those pieces of information in there. Okay, you can see my numbers. If I scroll way down to the bottom here, okay, come up to my last value. It says, all right, the 30th value was the number 10. There it is right there. Okay, and then there's nothing in the 31st value because I haven't input anything. It always just does that. In any event, in list 4, I've got my raw data. Okay, and if I want to look at the graph of these histograms, we can do that here. Okay, so we're going to go into a stat plot, which is right up here. So you're going to have to go second stat plot. Okay, second y equals. It brings you into this screen. We're going to go into plot 1. Right now it says it's off. Just hit enter. Okay, and we're going to turn this on. So now if I down arrow, I can choose different types of graphs. Okay, this is for bivariate data, which we'll likely use in Chapter 5. These are our histograms, and these are box of whiskers, which we'll talk a little bit more in Chapter 4. But right now, we're interested in the histogram. So I'm going to arrow over to the histogram, and I'm going to hit enter. All right, and now this information down here changed a little bit. We have to tell it which list of data. Now, most of you probably have this in L1 if you're playing along. I happen to have it in L4. So the L1, 2, 3, and so on are up above the numbers 1, 2, 3, 4, 5, and 6. You just have to hit second first. So I got to tell this, I want my data is in list 4. So I'm going to go second 4. Now, this should be the number 1 right now. Okay, 1 meaning we're counting each element in this list once. Okay, now you notice when I tried to hit the number 1, what happened? I get the letter Y up here, which is just above 1 on the right. See the letter A on here. Well, for whatever reason, my alpha lock is on, is kind of by default. So if that happens, I just hit this alpha button and it goes back to a regular cursor. Now I hit the number 1 and I'm good. Okay, so all that, I got all my information here. I'm going to do a histogram using list 4, and I'm going to count each element in list 4 once. Okay, how do I look at the graph? If I just hit graph, it may or may not work. What you really want to do is this: you want to go zoom, and you want to go down to number 9, zoom stat. This is how we look at our statistics graphs on the calculator. Okay, now you can go down at this point and hit enter, or as soon as you hit the zoom button, like I just hit zoom and I'm here, I can just hit the number 9. And there's my histogram. Now, the histogram isn't quite right yet. We have a number of partners that goes from 1 until 12. Well, if that's 1, 2, 3, 4, 5, 6, 7, we're not seeing 8, 9, 10, 11, 12, right? And I'm not saying that that's necessarily even 1, 2, 3. What we need to do is we need to fix this to capture our data. And do that by going to window. Okay, so we've entered our data into stat, into whatever list we've chosen. We went to stat plot. We turned our plot on. We selected histogram. We told it where to find the data, and we're going to count each data piece once. Then we did our zoom 9. Okay, and that's how we got to this point. All right, now we got to adjust the viewing window. So we're going to hit the window button. All right, now the lowest value in our data was 1, and the highest was 12. Okay, so our x min is 1. And our x max was 12. 12 was the highest value here. I want that to be 1, and I want this to be 12. Scale, what are we counting by? Well, for this, we're counting by ones. Okay, that's what we're counting by. Y min, this is how high up and how low you're going to go. So we certainly want to go up to what we have the most of. And now we're kind of cheating a little in that we can see the highest frequency was 7. 7 partners and 7 of them had that. Okay, so that's the highest value here. Again, these are going to be our tick marks. Excuse me. Let's do this. Max was 7. Okay. Min, you might wonder why are we not starting at 0 for the min. You can. I'll explain. It'll make more sense when I bring the graph up. I usually go down a little bit into the negative zone. The scale is what our tick marks are. We can count by 1 here, up and down. Okay. So now if I hit graph, let's take a look, and there's almost the whole story. Okay. Notice, because I'm going negative, what that does is it leaves a little bit of room below the graph, and that's for if I want to use this trace feature. Okay, so if I use the trace feature, it gives you some information down here, which I want to explain to you. Now, if I start at y, if I do a y min of 0, and I go to use my trace feature, notice it's kind of like overlapping with the graph, and it's a little clunky looking. Okay, so what I typically do is I typically go a little bit down into the negative side, kind of relative to my y scale, whatever my scale is. Maybe I go down that much or by like double that, right? Down 2, right? But it's giving me a little bit of room here. Okay, now when I hit my trace, a few things happen. Cursor pops up here. It tells you the min value of this. These are considered intervals. All right, the min value from here to here is 1, and it goes to less than 2. So basically, this goes from 1 to 1.99999. Okay. Now the point of this is like, while this graph is for discrete data, maybe we're not talking discrete data, which is nice about this. We can use this for continuous data too. Maybe we're talking about the number of pounds something weighed at birth. And so that could be any weight from like 1 pound to 1.9999 pounds, or even 1.99999, and go as far as you want with that 9. And when you get to 2 pounds, we pick up at the next block, 2 to less than 3. All right, so in any event, this is going from 1 to less than 2. Realistically, just the whole number 1 there. If I arrow to the right, okay, and move to the next one, 2 to less than 3, really just the whole number 2. And the end value shows you the number in the frequency. Okay, so again, back here, the 1B had 1 partner. In terms of 2 partners, there was 1B. In terms of 3 partners, there was 1B. 4 partners, there were 3 Bs that have 4 partners. Okay, 5 partners, there were 2 Bs. And again, everything matches up here. Okay. If I go like, one thing I wanted to going to show you here before I forget. Look, if I keep going all the way to the right, we should get up to 12 Bs, right? So I'm on 9, 10, 11. Get to the right, we'll see 12, and there's a 1, but the cursor's moved off the screen. So for whatever reason, when it comes to the X max, you want to really go above. And that actually has to do with like the intervals for the continuous data. I'm not going to talk too much about that, but the thing to know is that for X max, you always want to go 1 above your max value. Okay, hit the graph. Now we see the whole story. Okay, if I trace along, we can see we've got it all. Okay, 12 partners, only 1B had 12 partners. 1B had 11 partners. 2Bs had 10 partners, so on and so forth. Okay, so in any event, that's how you graph this given the raw data. All right. If you want to change the intervals, that's actually pretty easy to do here. I can go into window, and that is just your X scale. Your X scale is what you're counting by. So if I want to have intervals of size 3, 1, 2, and 3, I can make that a 3. And then if I hit graph, you'll notice a couple things happen, okay? One, it looks a little blockier, and these intervals have changed. And two, I don't see the top of this anymore, okay? And that's because these frequencies, these Y values are going to be a little higher now. We're counting the total number of Bs that have 1 through 3 partners. We're counting the total number of Bs that had 4, 5, or 6 partners, like we discussed earlier. In terms of changing the Y max, you don't have to work too hard to do that. I mean, we see it's 13 here. You can just use your trace for that. So on the first interval, we're going from 1 to less than 4. So that's 1, 2, and 3 in terms of the whole number of partners. And there were 3 Bs that had that many partners. If I go to the right, 4 to less than 7. So 4, 5, or 6 partners. There were 10. I go to the right again, 7, 8, or 9 partners. There were 13. And now I'm back down to the last one. But in any event, as I use my trace feature, I can see the largest value here is 13. And so let me just max Y out at 13, and we'll see the whole picture. Okay? Simply changing the X scale will change your intervals. Size 2, 1 or 2, 2 or 3, 3 or 4, 4 or 5, 5 or, so on and so forth. Okay? All right. Another thing we can do is if we actually have the frequency distribution in front of us, we can do the same sort of thing. We can graph this stuff as well. Okay, so I get back out of this. Now let's suppose I'm going to go into stat and I'm going to enter this data in, the actual X values and their frequencies. So if I go stat, edit, this is what I actually did earlier, in lists 1 and 2, which is why I went over to list 4. Do the raw data. Okay, so in list 1 I have 1 through 12, these guys. In list 2 I have the corresponding frequencies, okay, 1, 1, 1, 3, 2, 5, 7, and so on. All right, so we can do that. We can graph that, and you might imagine it should look pretty much the same, and it should. Let's see if I go stat plot, enter. Now my X list was list 1. And the frequency list is list 2, so that's what's different. I'm not using the raw data now. If I have the frequency distribution, this is the frequency. So what I want to tell the calculator is, okay, list 1 is the actual value, so to speak. Frequency list is the number of times they show up. I have that now. I put it in my list 2. Okay, hit graph. What do you notice? It's the same exact graph we saw a moment ago. Okay, because it's all the same information. Let me change my window back to 1. And let me change my Y max back to 7 just to get a good view at this. Okay, there's the same exact original graph. Okay, so you can either graph from the raw data, you can graph from the frequency distribution. Last thing I'll show you in terms of the calculator is if you want to graph the relative frequency. We saw it down below that the graphs basically look the same, right? Frequency versus relative frequency. Here's ours, our frequency. They look identical. Okay, how do we do the relative frequency? Well, the only difference is now, let's see, we'll go back into stat, edit, and I'm going to put the relative frequencies in list 3 here. Okay, so here's these numbers. Now I can sit here and type each of these in. All right, I can go 1 divided by 30 enter, 1 divided by 30 enter on the calculator here, like this. I go 1 divided by 30 enter, right? And I can do that for each of these. That's kind of tedious. I'm not going to do that. Okay, there's a more efficient way. So you arrow up right to the top here. Okay, I'm going to clear that out. Come in here. There we go. So make sure everything's clear. Get up in here. Okay, it's highlighted. And you get this L3 equals. Well, basically, what do I want to do? I want to take each of these frequencies and I want to divide by 30. I want to take each of these values that's stored in L2 and I want to divide by 30. So I can program that. I can go, look, take all the values in L2, second L2, divide them by 30. All right, so it's going to pick up each of these numbers, divide it by 30, and pop them in here. And there we go. So we got it all in there. Okay, and you can check these against what's over here, and it's all good. I'll match up. Now, one little point the book makes is, look, for relative frequencies, we're talking percentages here, so it should always add up to 100% or the number 1. When we round, sometimes we're off due to rounding by just like the slightest little bit. So like a 0.999, not uncommon. Sometimes a 1.001, not uncommon. Again, it just came down to rounding. Okay, so don't be surprised if it doesn't always exactly equal 1. It'll be like pretty darn close. All right, so in any event, back to the graphing. Okay, so now we want to graph the relative frequency. So I want these L1 values graphed against the L3s. So the only thing we have to do here when we go into stat plot is simply change where we're drawing our frequency from. We want the relative frequency, which I put in L3. All right, now when I hit graph, notice we don't really see much. Okay, we've got kind of like mine just shows a little line here. And it's not that the calculator did anything wrong, it's again that we got to adjust our window. Okay, keep in mind these are whole numbers going up to 7. These are frequencies, okay, relative frequencies that don't go very high. I mean, in total they add up to 1. So we really want to tone this space down a bit. All right, so again, if you're not sure what the highest value is, here we can see in the data it's 0.233. Use your trace feature, hit these numbers, and I'm just looking at the n value that's the greatest. Okay, there's the 0.233. That seems to be the biggest of the bunch. Everything else is pretty small. So when I go to window, max it out around there. I'll go 0.25 because it's just a nice number. I'm going to pick an appropriate scale, my tick marks. Okay, maybe like 0.01 or even 0.05 will be my tick marks. And let's take a look at the graph. Okay, we can kind of see this general shape. There it is, kind of looks like what we saw before, but we got an awful lot of empty space down here. Well, again, that's because we told the window to go down to -2 still. Okay, and if we're only counting by fractions of units here, we're only going up to 0.25, right? -2 is like really big compared to 0.25. So I just want to tone that down a little bit here, this negative value. So the comment I made a little bit before is like I usually use like my Y scale. So if my Y scale is 0.05, maybe I'll double that to like 0.1 on the negative side. Now that leaves just a little bit of room if I want to use the trace feature to easily read what this stuff is telling me. And now we got the number of partners and we have the relative frequency. In our sample, 10% of our bees had 4 partners. Okay, just a little more than 6.5%, 0.666, right? 0.06. So that's like 6.666%. Bees had 5 partners. Okay, so in any event, you can use this. I find you can do histograms in Sheets and Excel. Excel's probably a little easier to format than Sheets is from my experience, but you can also do it right here on the calculator. Okay, and so, read through the rest of the text. It does get into the continuous data right here. And again, the thing just being realizing that we're just talking continuous intervals, like, things like time or weight. They use an example here for suitable class intervals for carry-on luggage weight data. A piece of luggage might weigh anywhere from 0 to 30 pounds. And they're using intervals of length 5 here. So they'll randomly select some luggage, they'll weigh it, maybe it's 7.89927 pounds, in which case it'll end up right here in this interval, okay? And these intervals represent, basically 0 to 4.99999, as far as you want to go with your nines, as far as your measuring instrument is capable of measuring, okay? But as soon as you get to 5, you're now up in this next interval. to 9.9999 pounds. Once you hit 10, you're in this next interval. Okay, but again, you can set it up the same way on the calculator. You input your raw data, or you use your your frequency table if you happen to have one in front of you, like we did in the last example here with list 1 and 2. Okay, and then you mess around a little bit with your scale, and those are your intervals, like I said before. All right. They can do another example down here, very easy read. Take a look at that. Okay, and again, when do we use these? Well, we make histograms when we're dealing with continuous numerical data. Again, it works well for large data sets. Same thing, be careful with your boundaries, use labels, make sure you're clear, use appropriate scales, draw the rectangles, okay, appropriate to the, or proportional to the areas of the rectangles need to be proportional to the frequencies or relative frequencies. Okay. Now, what do we look for when what's the big deal with graphs in general? Well, again, it should be a visual way to kind of quickly get some information about the data. All right. Things we typically look at are the center, or what we call a typical value. Where are these things peaking? Okay. Okay, the typical number of partners is arguably between, like, 6, 7, or 8 for these bees. This is peaking at 7. This was 6 partners. This was 8 partners. I would say that the typical bee probably has 6, 7, or 8 partners. Okay. The extent of variability. How spread out is the data? How far left and right are our variables? Okay. We'll talk more about that in Chapter 4. We'll talk a lot more about center as well in Chapter 4. General shape we're going to talk about in a moment. Look at the general shape of this graph. Okay, this one kind of goes up and then comes back down. It kind of bumps up and down a little bit here and there, but in general, it kind of goes up to the center, comes back down. Location and number of peaks. Here's a peak. Here's a little bit of a peak here. Okay, and presence of gaps and outliers. Well, there's no gap. The gap would be when the bar doesn't go up at all. Like if there was like let's let it just to show you. If I go into real quick stat edit, and let's say there was like, no bees had exactly 2 partners. Okay, I don't know why that didn't change, but let me see. Stat. Oh, because I didn't change it to L2. That's why. Going down. Stat plot, graph it against L2. Okay, we're back to the actual frequencies. Let's see if this will work now. Yeah, okay. So look, I just took that out, and that's called a gap. An outlier, again, we'll talk more about in Chapter 4, but an unusually large or small value in the data. Okay. 2 people making reasonable and similar choices for the number of intervals, the interval width, and the starting point of the first interval will usually obtain histograms that are similar in terms of center, shape, and variability. Okay, there's another example here. This is using continuous data. Notice how they wrote the intervals. That's kind of the only point I want to make with this. Looking at sleep deprivation. Okay, -6 to less than -4. Okay, so -6 to just about -4 out. Anytime I'm over -4, like -4.1. But now -4 to less than -2. -2 to less than 0. 0 to less than 2. Anyone who got who was deficit from 0 hours to 1.99999 hours. Okay, but once you hit 2, you go to the next interval. So in terms of showing your intervals on paper, it's not uncommon to see the less than symbol, so that's clear that once you hit 6, now you're going up to the next interval. Okay, but again, you can kind of take a look at that. It should be relatively straightforward. We don't get too into class intervals of unequal widths in this course. Feel free to read through this, but I will not be assessing. But what we do need to talk a little bit about are histogram shapes, okay? General shape is an important characteristic of a histogram. In describing various shapes, it is convenient to approximate the histogram with a smooth curve, called a smooth histogram. You'll see You'll see me do some drawings like these as we move throughout the course, particularly when we get into normal distributions and areas under those things and whatnot, okay? But these are going to become common. So what you guys are going to start doing is given a histogram, which is made up of these rectangles, you'll want to kind of see like a curve that can be drawn to resemble that histogram, okay? Approximating a histogram with a smooth curve. So again, if we start with like this particular histogram, more or less, we're kind of going through the midpoint of each of these peaks, not so much right here, but that's why I say more or less to draw this smooth curve, kind of peaks out right here and comes down. Okay, so again, these smooth curves are just kind of like a way to mimic these histograms. Okay, now one description of general shape relates to the number of peaks or modes. Okay, mode is the most frequently occurring value. Unimodal is a histogram that has a single peak. Bimodal is if it has two peaks, and multimodal if it has more than two peaks. Okay, so here's an example of an unimodal. Again, picture like rectangles under here, and the general shape of those rectangles creates this smooth curve. But here's unimodal, one peak, bimodal, two peaks, and then multimodal because it has numerous peaks. Okay, more than two. Symmetric, a unimodal histogram is symmetric. Okay, a single peak histogram is symmetric if there is a vertical line of symmetry such that the part of the histogram to the left of the line is the mirror image of the part to the right. If I can draw a line vertically through the middle and they match up the two sides, we have symmetry. Okay, it doesn't have to be unimodal, it can be bimodal. Okay, now careful here in terms of shape. Okay, skewed. A unimodal histogram is not symmetric is described as skewed. Positively skewed or right skewed. A skewed histogram in which the upper tail of the histogram stretches out much further than the lower tail is described as positively skewed or right skewed. When we talk about the tails, we're talking about these things, the left and right sides, as these graphs go out to the left and right. Okay? So positively skewed, the upper tail, the tail on the right, stretches out farther than the lower tail. Okay, that's graph A down here. The bulk of the data is actually down here. If I'm drawing these rectangles in representing the histograms in here, okay, try to visualize that, I might have like one little rectangle up here, or an outlier, so to speak, some unusually large piece of data up here, where the bulk of the data is here. This outlier forces me to pull this tail out longer. Okay, this is called positively or right skewed. We're bringing this out here. There's some unusually large value way off to the right of our data, pulling the tail over, right? That's the idea, okay? An example might be like salaries of like Walmart employees. The bulk of your Walmart employees are probably making, maybe some are making minimum wage down here, and then you get some that are making okay, decent money, I guess managers or whatnot, maybe 15, 20 bucks an hour, whatever. But then you got like your CEO who's bringing in huge amounts of money, right? And he's like an outlier way up here. And so when I draw this curve, here's the bulk of the employees, and there's this guy probably way out to the right here. I can't even probably get out far enough to the right that's making boatloads of money. That would be skewed right. Okay. On the other hand, negatively skewed or left skewed is when the lower tail, the left tail stretches out farther than the upper tail. Okay, that's this blue one here. The bulk of the data is here. There might be some unusually low value in our data set that when we go to draw in the smooth curve is forcing us to extend this tail to the left. Okay, an example of this I find honestly are like grades for students in AMAT 108. Most of my students get A's, B's, decent grades somewhere in here. And then there's always a few that do really poorly. They stop doing the work, they bail out, they don't turn things in. And so those one or two students, these grades are down here. And so when I draw the histogram, okay, A's and B's, not too many C's, and then I got somebody way down here that I need to account for. And that's called negatively skewed. Okay, we'll talk more about skew as we go through the course, but just have a general idea of these shapes. It's easy to reverse them. Positively skewed, we We pulling out to the right, negatively skewed, we're pulling out to the left. Something we spend a lot of time talking about in this course, particularly in later chapters, is a normal curve. Okay, and that arises more frequently than any other in statistical applications. Many histograms can be well approximated by a normal curve. For example, characteristics such as arm span and the weight of an apple, that was a previous example. Here we briefly mentioned several of the most important characteristics of normal curves, postponing a more detailed discussion until Chapter 7. A normal curve is both symmetric and bell-shaped, and it looks like the curve in the figure below. However, not all bell-shaped curves are normal. In a normal curve, starting from the top of the bell, the height of the curve decreases at a well-defined rate when moving toward either tail. The rate of decrease is specified by certain mathematical functions. Okay. So anyway, in any event, here's three relatively normal-looking curves. I typically draw them usually looking like A. Here's one that has, they're calling it a little heavy-tailed. Here's one that they call a little lighter-tailed. I wouldn't get bogged down with these specifics, okay? But know that in general, a normal distribution or a normal curve takes on this bell shape. Okay, peaks in the middle, it is symmetric about the peak. I could cut this in half and fold it over itself, get a mirror image from left to right. Okay, peaks in the middle and tails off. Most of the data, here's my rectangles again, representing, the area is proportional. The vast majority of the data is near the center. A very small amount of the data tends to be very far away from the center. The further away you go, the less data you tend to see. Okay. Now, do sample histograms resemble population histograms? So a big part of the course, particularly in the later chapters, 8, 9, and 10, focuses on using sample data to make generalizations to the population at hand. So how good of a job do sample graphs do compared to the actual population graph? Okay, sample data are usually collected to learn about a population. Conclusions based on sample data may not be correct if the sample is unrepresentative of the population. So how similar might a histogram of sample data be to the histogram of all population values? Will the two histograms be similar in terms of center and variability? Will they have the same number of peaks? And will the peaks occur at approximately the same places? Right? Again, that's important. We went out, we took a random sample of a population, we wanted to know something about it. If we look at the data and we make a graph with the data, will it accurately model the population? Can we draw some conclusions? I don't know. A related issue concerns the extent to which histograms based on different samples from the same population resemble one another. If two different sample histograms can be expected to differ from one another in obvious ways, at least one of them might differ substantially from the population histogram. If the sample differs substantially from the population, conclusions about the population based on the sample are likely to be incorrect. Okay, and that's kind of the point I was making a moment ago. Sampling variability, the extent to which samples from the same population differ from one another and from the population, is a central idea in this course. Okay, and in the science of statistics. All that means is, look, there's a population. Say, like, we're interested in the average length of the fish in the Hudson River. I can go out and try and catch 10 fish, and I can measure their length, and then I can take the average. You could go out and catch 10 fish, measure them, and find the average length. Are your 10 fish likely going to be the same as mine? Probably not. Is your average of those 10 going to be the same as the average of mine 10? Probably not. That's the idea behind this sampling variability. Different samples from the same population inherently tend to differ from one another. Okay. So, you can read through this example, but what we have here, just to kind of cut to the chase, is we have a population histogram. Okay, this is the number of accidents and the relative frequency. What are we dealing with? Bus drivers, I think. Yeah, no, frequency distribution for number of accidents by bus drivers. Okay, 117 have had none, 157 had one, so on and so forth. Okay, here's the actual graph of the population. And so what the example shows is, suppose we took random samples from this group. This is a large group, okay? I mean, you can see these frequencies get pretty big. There was 708 observations. Let's suppose we take a random sample of size 50 observations from this population. Okay, so that's the idea here. We have 708 slips of paper in a bag. We're going to pull 50 of them. What's on the bag is the number of accidents those people have been in. So there's a lot more pieces of paper with, say, the number 2 on them. There's 158 slips of paper with the number 2, 157 slips with the number 1. There's only 21 slips with the number 6 on there. So some of these are going to be much more likely to randomly select than, say, these numbers, okay? Just because there's so much more of them. But the idea here is, look, here's the actual graph of the population. Now if we take a random sample of size 50 and we make the frequency graph for those, here's what 4 such samples look like, okay? So they went in and grabbed 50, this is sample histogram number 1. Number 2, number 3, and number 4. Okay, so let's try to compare to the population. Now the population is certainly skew right. The vast majority have had between 0 and say 3 accidents. And then we have these very few occurrences of high values bringing the tail region off to the right. So we have a skewed right distribution. It peaks around 2, 1 or 2, unimodal, okay, and the variability goes from 0 to 11. Let's take a look at these. This peaks around 1, arguably around 1 or 2, and the highest point is right at 1. There's the mode, okay? And it seems, even though it kind of goes up and down a little bit here, in general it seems to be tailing down to the right. Now this sample had much less variability, okay? But again, I mean, how many slips of paper actually had the number 11 on them? If I want to see that data, I think I can see it right here. One person was in 11 accidents. 3 people were in 10. 1 person was in 9. So of these 708 slips of paper, it's not very likely that you're going to grab some of these numbers. These are the much more likely ones you're going to grab in a random sample. So it kind of explains a little bit less variability, but in general, you know, it peaks around the same place. And you can kind of see this skewness to the right. As it goes to the right, these values tend to decrease. Okay, and a little bit less variability. Arguably here, the same thing. This one happened to have a lot more zeros in the sample. Okay, not a real unusual occurrence. A good amount of the population had no accidents, about 16%. But again, it's peaking on the low end. Okay, and it does indeed tail off to the right a bit. A little bit less variability than the original population, but that's normal for samples to do that. You'll understand a little more why back up in Chapter 8 when we get there. Okay, but in general, it's peaking around the same area, and again, it's skewed to the right. This one, I'd say, peaks a little higher, around 2, but again, skews to the right. A little bit less variability than the population. This one's peaking around 2, and again, skewed to the right with a little bit less variation in the original. Okay, so in general, while these don't exactly look like the population, okay, they're reasonable models. They peak around the same region, and they have the same general shape, okay, slightly skewed to the right, these things are. So what does that mean? Well, the original question, you know, up here, do sample histograms resemble population histograms? Often they do. Often they do if the samples were chosen correctly, like the things we discussed back in Chapter 2. If we have nice random samples, then yeah, you know, these samples can yield reasonable models to the population. Okay, we're not going to get too into the cumulative frequencies and the frequency plots either in this class, but feel free to read into it to have a better understanding. But that just about wraps up section 3.3 and for the most part chapter 3. So you guys should be able to work on your web assignment, and as always, reach out to me if you have any questions on content or anything else. All right, folks, have a great day.